Okay, in this video we're going to take a look at the integral, which is the opposite of a derivative. So if we look back at the derivatives that we were doing, for the derivative we were just taking the slope of the y and x axis. And you can see that you divided the y-axis by the x-axis. Dividing the two axes gives you the derivative. Well, for the integral, it's the opposite of the derivative, it's the opposite of division. We're going to multiply the x and y axis to get a value for our integral. So an integral is an infinite sum. We did integrals with value. Before. Let's look at a very simple velocity as a function of time graph. And 1, 2, 3, 4, 5. And I can start here. Bam. Okay. So if we look at this graph, similar to something we've looked at before, in order to take the integral of this, we have to add up the area that is underneath the curve. So underneath the curve is from the line to the axis. So what we would do is break this apart into different sections that we can calculate the areas of and add them all up. So I'll give a couple values here. So 1, 2, 3, 4. Keep it simple, but if we look here, we can break this apart into one rectangle and one triangle. So we can find the area of both of them. So this is 1 meter per second times 5 seconds. So we'll have 5 seconds times 1 meter per second. You can see the units cancel out to give us 5 meters. So that's section gives us a displacement of 5 meters. And we can do 1/2 the base, which is 1/2 5 seconds, plus the height, which is 3 meters per second. Again, the seconds cancel, we end up with meters. We have 7.5, which is half of 15 meters. To get a total distance that this object would travel if it started with a velocity of 1 meter per second, changed it to 4 meters per second in 5 seconds. It's pretty simple when we have straight lines and triangles, but it's not always going to be that easy. What happens if we have a graph that does that? So we cannot, and it's not a perfect circle. What we'd have to do is we sum up all the different areas. So for the previous graph, pull that back over here. Okay, we're basically doing a summation of all of the areas within this graph. And I'm going to ignore my phone, so let's see if we can get through this. Okay, sum up all the areas. Well, we can calculate the area of those shapes. Well, we have to do the same thing, but sum up all the areas that we are going to shrink down. So what we would do is we would basically break this apart into little bars and estimate how much we go under and how much we go over when adding up all these shapes. Not a very effective way to do that. And if we shrink these things down smaller and smaller and closer together, we'll end up with an infinitely small width there. So that's where we get the infinite sum. The symbol changes from a sum. This is for a large sum, similar to a delta symbol for large change, to a small change. We use, since this is sigma, which is an S, stands for sum, we use an integral sign, which is a really elongated hook-looking S. Okay, this is an infinite sum. So we would take the integral of the function v of x. And if we think back to what we just did here, if we summed up all the areas here, we got units of meters, which was displacement, or change in position. So that the integral of the function of v of x is going to give us, and actually that's wrong, that's not v of x, that's v of t, is going to give us the position as a function of time. All right, which is the opposite of the integral. The dx dt gave us velocity. The integral of velocity gives us position. Okay, and we did these a little bit last year through our graph conversions. So if we look at this, we know that our object's going to start with a positive velocity. That velocity is going to decrease to 0, and then it's going to increase negatively. We do not know where this object's starting, so it actually doesn't matter where we start a position. We can imagine it starts at a reference point of 0. In order to have a positive velocity, we're going to have a positive slope. And that positive velocity is decreasing, so our positive slope is decreasing until it reaches 0. Then it increases negatively from 0. So 0 slope to an increasing negative slope. All right. So this is an velocity time graph of the velocity of an object that is thrown up into the air. It reaches its maximum height and then falls back down. So that's the idea graphically for an integral in terms of velocity and position. And here, again, we can say that the integral of velocity as a function of time will give us position as a function of time. And if we take that one step further here and draw our acceleration as a function of time graph, this is clearly a negative 9.8 meters per second squared acceleration graph. That's constant because gravity. But the integral of the acceleration as a function of time will give us velocity as a function of time. So these are the ideas that we have to remember when thinking about position, velocity, acceleration. Even when we get into other things like force and energy, we got to make sure that we know frontwards and backwards what the derivative and what the integral will give us. So what we'll most likely see with an integral is we'll be given the velocity function or the acceleration function, and we'll have to figure out where our object is. So let's look at the specific math to this, and I'll put that in the next video here.